So based off of your data from the living periodic table, where you compared an element you were sitting at to the elements around it, we should be able to find some overall trends along the periodic table. Now there are some slight exceptions for each one of these trends, but we will look at an overall trend going across an entire periodic table and going up and down the entire periodic table. So for atomic number, as we go across a period, remember when you write a sentence, you go from left to right and you end it in a period, so periods go left to right. As we go across a period, our atomic number increases. And as we go down a family, our atomic number increases. Atomic mass should follow this same trend because our mass is based off of our protons plus neutrons. So if our number of protons is increasing going across a period, then my mass should be increasing going across a period. And my mass should be increasing going down a family. Next we have atomic radius. So radius is just like when we're talking about math and we're talking about in geometry how wide something is based off of a circle. Our atoms have a general circular shape, so our radius is how wide they are. The way that we calculate radius is it is half the distance between the nuclei of two like atoms. What that means is if I have a fluorine and another fluorine, an easy way for me to find the radius is I can see this dense nucleus whenever I zoom in a microscope, and halfway between the two should be the width or the radius of that atom. Okay? So my atomic radius is half the distance between two nuclei of like atoms. Now atomic radius going across a period, it decreases. Now when we first look at this seems strange. We just said that our mass increases going across a period, but our radius decreases. That is because our mass is based off of our nucleus. Okay, this entirely comes from our nucleus, which is the really tiny, tiny, tiny small thing in the middle of the atom. The nucleus has no effect on the radius. My radius comes from my electron cloud. So these are independent of one another. You can weigh a lot but be very wide based off of your electrons. Okay, or you could weigh a lot less but be wider based off of your electrons. The electrons don't weigh anything. It's like wearing one of those airy blimp suits. Okay, the more you pump up air in there, the wider you get. It doesn't really add any mass to you. Okay, so they're entirely two different things. The electron cloud has practically no mass. The mass is all going to come from your nucleus. So then what is it that changes the size of my atomic radius? Now I had you draw this picture. And the reason is I want to be comparing each one of these as we go across a family. So I'm going to start with lithium. In lithium's nucleus, I have 3 protons. And on the first energy shell, I have 2 electrons. 1, 2. As I go across each one of these, 1, 2, has a full S shell, and therefore has 2 electrons on the first energy level. 1, 2. Now I want to compare the next energy level. So everyone has 2 electrons on the first energy level. We're going to compare the next energy level. On the next energy level, I only have one electron here. And I want to just compare one electron for each one of these. This one electron is going to be pulled on by 3 protons. So it's going to be held in. The radius of an atom is going to be based off of the pull of the protons on this one electron. So if I compare lithium and boron, lithium has 3 protons in its nucleus, and boron has 5 protons in its nucleus. So if I'm just comparing one electron on each, who should be able to pull in this one electron further? 3 positives or 5 positives? 5 positives. So if I draw my next energy level, it shouldn't be as big because this one is going to be pulled in a little bit closer. Now if I look at my next one, if I compare boron and nitrogen, boron has 5 positives, nitrogen has 7 positives. Nitrogen should be able to pull in this one electron a little bit further. And this continues going across the entire period. Each time we go across the period, if I keep going to fluorine, fluorine now has 9 protons. So these 9 protons are going to be able to pull in this outer shell even more. So this one valence electron is closer and closer and closer. Now we know that each one of these has more valence electrons on its shell. Lithium only had 1, but boron should have 3. And each one of these are going to be pulled in the same way. Because each one of these on the same energy level, they're not interfering with each other at all. This electron isn't blocking this positive pull from this electron. It's not going to matter how many valence electrons there are because they're all on the same energy level and they're not going to block each other from this positive pull. So what matters when we're pulling in going across here, and nitrogen's the last one we'll do, 1, 2, 3, 4, 5, 6, 7. They are not blocking each other from this positive pull. This positive pull is getting larger and larger and larger and pulling these electrons in closer and closer and closer. So therefore, as we go across a period, our atomic radius actually gets smaller because my mass and my electron cloud are independent of one another, their sizes. Think of a magnet when you're thinking of this because we have positives and negatives and their attractions. Now, for my next one, if I want to compare going down a family, on sodium's first shell, it has 2 electrons just like everybody else. On its next shell, it has a full second energy level. So 1, 2, 3, 4, 5, 6, 7, 8. And then on its third shell, it's going to have 1 valence electron. Going down a family, my overall radius is going to get larger because you're adding an entire energy level. Okay? So going down a family, we get larger because we're adding an entire energy level. So let's put that in our notes. So atomic radius increases going down a family due to the addition of an energy level. We're adding an entire ring. That's obviously going to make it wider and wider. Now, electronegativity is the measure of the ability of an atom to attract or steal an electron from another atom. looking at your data, it increases going across a period. Once again, if we look back up here at this increase in the proton pull, that makes sense. It's the ability to attract an electron. This has 9 positives, that has 3 positives. This one will attract an electron much better than this one. More positive means more attraction. So going across a period, it should attract more. Now going down a family, while this one has more protons, these electrons are further and further away. The further and further away they are, the less able I'm going to be able to attract it. So going down a family, it decreases. Now when you look at these pictures, one of these 2 pictures is electronegativity. The only difference in these 2 pictures is this one, my noble gases have a lot, and this one, my noble gases have none. Well, electronegativity is the ability to attract an electron. My noble gases already have a full shell. Is there anywhere for a new electron to go? No, so my noble gases have 0 electronegativity. So this picture here will be for electronegativity. Label it. And an easy way to remember each of these trends is to get an overall arrow. We can see that going up, it increases, and going this way, it increases. However, we're going to stop at fluorine. My noble gases don't do anything. So my overall arrow, instead of memorizing several different ones, let's memorize one. Overall, we increase. If we start at the very bottom and keep going up, now draw the arrow so it gets bigger so you remember what the arrow means. Then we're going to stop at fluorine. Remember electronegativities in this general trend arrow, and you should be able to compare electronegativities. You should know automatically that oxygen is more electronegative than germanium because oxygen's further up on that arrow. My next one, ionization energy. This is the amount of energy required to take an electron from a neutral atom. So if I want to go take an electron from something, I'm going to have to add energy. I'm going to have to do something to actually attract that electron away from that positive nucleus. Once again, if we look at this picture, it's going to take a lot more energy to take an electron from fluorine with its 9 positive pull than from nitrogen with its 7 positive pull. So going across a period, once again, it's going to increase. And then going down a family, once again, these electrons are further and further away from that positive pull, so they're going to be easier and easier to take. Okay? So going down a family, it's going to decrease. All because we're adding energy levels, so our outermost energy levels are getting further and further away, and they're easier and easier to take. Then this next picture, down here, this represents ionization energy. Because the hardest one to take an electron from is going to be our noble gases. And specifically, the highest is going to be helium. Helium has 2 protons with 2 electrons directly beside it. It's going to take a ton of energy to try and steal electrons from that full outer shell right beside the nucleus. So this right here represents my ionization energy. And my overall arrow this time, this time we don't need to put a letter at the end because it doesn't end with a certain element, unless you want to put helium, but it goes to the very tip of the periodic table. Helium is going to have the highest ionization energy. It's going to be the most difficult to take an electron from. And now finally, we're going to talk about forming ions. Atoms become ions by gaining or losing electrons to become charged. An atom is stable when it has a full outer energy level, which would be 8 valence electrons, except hydrogen and helium, which only want 2 valence electrons. Atoms that lose or give away electrons become positively charged. I've lost electrons, so now I have more positives than negatives. Atoms that gain or steal electrons become negatively charged, because now they have more negatives than positives. Negatively charged ions are called anions. A negative ion. They have an ionic radius that is, I'm going to skip this, than the atomic radius, because the addition of electrons decreases the positive pull of the nucleus. By adding more and more and more electrons, that positive pull becomes less effective. Now, the positive pull is what decides the radius. However strong that positive pull is how strong you're able to pull in those electrons. If I'm less able to pull in those electrons, my radius becomes larger. So the radius is larger. Now, my positively charged ions are called cations because they are positive. They have an ionic radius that is smaller than the atomic radius, because the loss of electrons increases the positive pull of the nucleus. So down at the bottom, my last picture, we're going to talk about ionic and atomic radius. All the elements in the top left corner are what they look like without a charge. So you can easily see why my atomic radius, starting here, my atomic radius gets much larger going in this direction and much larger going down, which gives my overall atomic radius, looks like this. Atomic radius increases going down. And my ionic radius well, we said there's a difference between my anions and my cations. So if I draw my stair step to divide them up, on this side I'll have my anions, and on this side I'll have my cations. And my arrow does the same thing as atomic radius, but it restarts at the metalloid line. So when you cross this metalloid line, we restart at being really, really tiny again. Remember, my anions get much larger, and my cations, they still get larger going down, but they were much smaller than their original. So I'm going to reset at the metalloid line. So these trends right here, especially these 4 that we drew the arrows for, these will be heavily tested and you really need to know and understand them. These notes will be on YouTube if you need to re-watch this several times to kind of go through it. And we also have a couple of helpful videos in your homework. This page is not homework. Go to the next page. This page is homework. You need to watch these 2 videos, and you need to answer all of these questions.